Okay, I think we'll get started. So again, thank you for joining us today. Today's session is going to be focused on a simple question. Why do some ceramics components perform reliably in high temperature environments while others fail much sooner than expected? Because in reality, it's rarely just the material. It's a combination of the selection, design, and operating conditions. And small decisions can have a big impact over time. That's what we're going to try and unpack today in a practical, real-world way. And just a quick note, we are recording this session. I'm Ralph, and I'll be moderating this today. I'm joined by Gary, who's the Managing Director of the Ceramics Division at Andaman and Company, and Richard, who's a Technical Commercial Engineer. Both of them work very closely with customers on real-world applications. So what they're talking about is grounded in reality and what actually happens and not just theory. The idea of this is to try and keep it practical, and we'll leave time for questions at the end. So feel free to drop them in the chat or the Q&A as we go. We'll come back to them at the end. So before we actually start on the questions, Gary, Richard, could you just give 30 seconds to introduce yourself to the audience?
Yeah, for sure. Good afternoon, everybody, or good morning for some of you. My name's Gary Hately, and as Ralph mentioned, I'm the Managing Director, newly appointed Managing Director for the ceramics business of Andamans. I've been with the company since 2009, held various positions, territorial manager through to commercial director, and spent a lot of time at the forefront working with our customers, both on opportunities, existing and new ones, and developing those into ceramic supply.
Yeah, good afternoon, everyone. My name's Richard Verrier. I am the Technical Commercial Engineer for Andaman Ceramics, dealing predominantly in the UK and EU and rest of world markets and the USA. I've been with the company for about 4 years now. Background before then dealing in materials engineering and materials research. So quite familiar with this quite niche industry. And as Gary meant, I work quite closely with Gary, dealing with a lot of customer inquiries, new business developments and new projects and new material developments.
Excellent. Well, thank you very much to you both. So let's get on with some of the questions. When we talk, Gary, about high temperature performance, what actually are the key factors that really matter?
Well, when people evaluate how a ceramic will behave at high temperatures, what they're really asking is, will it keep its shape, its strength, and chemistry under both heat and stress? And there's several key factors that will determine that. The first being the melting point and thermal stability. Ceramics value because of their high melting points, but what matters more is how stable they remain below that point. Some materials start to degrade, soften, or undergo phase changes well before melting. The second point I'd like to highlight is creep resistance at high temperatures. Even hard ceramics can slowly deform under load, a process called creep, and good high temperature ceramics resist this, maintaining their shape over long or longer periods. The third point is thermal shock resistance, which is the rapid heating or cooling, which can then sometimes crack ceramics. This is very much dependent upon thermal expansion coefficient. Generally, lower is better. And thermal conductivity, contrary to that, where higher helps distribute heat better. Materials like silicon carbides tend to perform really well in these kind of atmospheres because they can handle temperature gradients much better than some of its counterparts. The fourth element being oxidization and chemical stability. At high temperatures, reactions with oxygens or other atmospheric elements can degrade materials very quickly. The fifth point, mechanical strength at temperature. As strength usually decreases as temperature rises, the key is how much strength then is retained in the body of the ceramic. The sixth point, phase stability, and some ceramics undergo phase transformations when heated, which can cause expansion, cracking, or loss of strength. A stable crystal structure across the temperature range is crucial for this. And then we move on to microstructure, which is the fine grains can improve strength, but have an adverse effect when it comes to creep. So porosity generally reduces the mechanical performance, whilst being beneficial, however, in thermal cycling applications. And in certain environments, the control of the microstructure is often as important as the material itself. In practice, no single factor dominates. It's the combination that defines performance. That's why different ceramics are chosen for different roles.
Excellent. And Richard, when you're talking to customers, do you find that they often focus on one factor like temperature, and sometimes miss the bigger picture?
Yeah, I think that's definitely the case, Ralph. A lot of people will come to us and say they've got parts that they're looking to survive up to certain high temperature ratings, but then we will always have to go back to them with questions asking, say, how quickly are you rising to these temperatures? Because as Gary mentioned, factors like thermal shock play big roles in how well the material is going to perform, how well a part's going to survive in application. And so we find that so many times people will just say, here's one feature that we need the part to be able to do, without actually looking at every other factor that could influence the material in the performance over a lifetime. And so therefore it's all information that is critical in a ceramic component.
And so, Richard, what's from your experience, what actually is the most common reasons that ceramic components fail in high temperature environments?
There can be a number of different reasons. There's predominantly thermal will be the main one, where parts have exceeded maximum operating temperatures, so leading to heavy amounts of cracking. Thermal shock is also a very common one that we see, where parts have been heated or cooled from the maximum temperatures that they're working at a rate that the material is not capable of doing, causing very quick, very rapid crack growth in the material. But alongside the thermal, there's also mechanical issues that can form, especially at high temperature. Certain materials, and you'll see data sheets where it says a part is able to withstand a certain amount of weight at one temperature. However, this a lot of the time ignores the fact that when you then heat the parts up, as Gary says, they stay stable, but they will drop slightly. And if people are trying to load up weight too heavily, load up too much parts or too many parts into a component, causing too much bending or stress to be going through the material, it can often lead to cracking and failure within a part.
Excellent. So Gary, there's a lot to unpack there. So would you say, how often are these sort of failures down to design decisions, the specification, or just misunderstanding the operating conditions?
Yeah, well, in short, the aforementioned reasonings you've just given covers almost all of the explanations when critically analysing why a ceramic has failed in application. But we do have to be really cautious and careful when using the phrase ceramic failure, as it's not always the material that fails, but more so a case of the requested ceramic being the incorrect choice for the given application, which happens when atmospheric or application details are not fully disclosed to us at the point of inquiry or initial discussions around the new part.
Okay. Gary, you both mentioned thermal shock a lot. From someone that's from outside the industry, what does it actually mean in practice?
I think Richard touched upon it in one of his previous answers, but in essence, thermal shock is when something cracks or breaks because it's heated or cooled too rapidly. A simple way to picture it, or as an example, if you take a very hot ceramic mug and then suddenly run cold water over it, the outside cools and shrinks faster than the inside. That difference then creates stresses and the mug can crack. So thermal shock is the damage caused by sudden temperature change. And it becomes a problem anytime something experiences sudden temperature changes, especially if the different parts heat or cool at different speeds. Common situations include materials perhaps in furnaces or in kilns that have just been heated or cooled too quickly, and things like components in engines or turbines being exposed to rapid temperature swings, and things that are repeatedly thermal cycles can gradually cause cracking or premature failure.
Okay. And what, say, Richard, can people do early on to reduce this risk?
The easiest thing they can do, without saying too much about it, is to speak to the experts about this. There's lots of different materials and different ceramic grades that are available, each which have their own unique mix of properties, chemical compositions, and different strengths and weaknesses. And thermal shock is a big one where different materials will perform in different ways. And throughout a lot of experience within the industry, we've learnt where certain materials may survive in certain applications or certain ramp cycles. So making sure that you know your full thermal cycle is important. So knowing how quickly you're going to be heating and how quickly you're going to be cooling parts, and then being able to share that information with people who understand the materials that they're being supplying will help greatly in designing parts that'll avoid these issues.
Excellent. And you've touched on it there, but there are a lot of different materials. So how do materials like alumina, zirconia, silicon carbide behave differently in high temperature environments? And also, where do they work well, and where would you say they don't work well in each?
Well, each of the materials, as Gary mentioned earlier, each of the materials have got different properties and different strengths and weaknesses. For example, a fused silica may perform much better in a thermal shock environment than an alumina, but it's not just the material, it's also other features that are designed within it. For example, porosity is another feature that we can add to a material body that will help improve thermal shock resistance. As one particular example, so if you are pouring molten metal into crucibles, you would ideally want a porous material body to help the parts survive the very quick temperature change that may come from that. But also it's all about understanding the applications and the requirements, and that's the main things that will help you determine which material is actually suitable. Silicon carbides, for example, would be used ideally in alongside molten aluminium, whereas an aluminum may cause a lot more problems. So it's all down to understanding the application in the industry that you're using.
Okay. And so Gary, when you're out and talking to customers, do you often see customers asking for a specific material first, or do they come with a sort of a more open-minded sort of view on what they need?
Usually it's the former, and mainly this is down to legacy purchasing patterns, or in situations where the industry is highly regulated, where surface, or let's talk about metal, superalloy contact materials are scrutinized to the highest level because of the very nature of the application. So change is very, very difficult. And it's our job to help our customers understand that there are better material solutions available. And as we approach any inquiry with the freedom of being able to offer solution based on the requirement, rather than being dictated to by a limited number of available materials or forming methods, our unique selling point as a chosen partner is our ability to bring together the right material with the right forming method for any given application.
Okay. And what would you say are the most common design mistakes you see?
Designing with ceramics is tricky because they're strong, but they're not forgiving. So most failures come from avoidable design choices. Some of the more common mistakes engineers run into and things that we see are things like sharp corners and sudden shape changes. So ceramics don't handle concentrated stress well. Sharp corners or abrupt thicknesses changes create stress, hot spots where cracks can start and permeate from. Smooth transitions and rounded edges are far safer. When they assess a ceramic, or when engineers assess a ceramic, they look at it as if it's a ductile material, and it's not. Unlike metals, ceramics don't yield. They fail suddenly. Ignoring this brittle behavior leads to parts that work fine until they snap without warning. We talk about thermal shock, or we have previously during this webinar, and designs that expose one part of the component to rapid heating or cooling while another part stays at different temperature. This creates internal stresses, and thick sections next to thin sections often makes this even worse. Even wall thickness is key. Big differences in thicknesses cause uneven heating and cooling, and internal stresses during both manufacturing and use. Keeping thickness more uniform improves reliability. Again, coming back to creep at high temperatures, at elevated temperatures, ceramics can slowly deform under load due to creep. Designing as if the material will stay perfectly rigid can lead to long-term distortion or failure. One of the constant challenges we run into is over tight tolerancing, and ceramics are hard to machine and can vary and can vary slightly after sintering. Designing extremely tight tolerances without considering manufacturing realities increases cost, most often unnecessarily, and rejection rates. A couple more examples of design issues are bad joining methods, where engineers are trying to bolt or clamp ceramics like metal, and this can introduce local stress points. So poorly designed joints often become failure points, and interfaces need to have load distributed gently. Surface finish or surface damage and neglect, small scratches or machining flaws can act as crack starters. So since ceramics are sensitive to surface defects, finishing and handling matter a lot more than people expect. And all these factors we build in to when we work with our customers to offer a solution for an issue that they're facing. So, in summary, most ceramic failures are because the material aren't because the material is weak. They're because the design doesn't respect how ceramics behave. If you design to avoid stress, concentrations, manage temperature change, and accept brittleness, performance improves dramatically.
Wow, so there's a lot there, Gary. And so Richard, from a technical point of view, how early should customers be thinking about these factors in the design process?
It should be right at the start of the process, Ralph. One of the things we do as a ceramics supplier is every time we get new customer projects or new parts, if there are any drawings or knowledge about what the actual part needs to do, we will discuss and we will help the customer design that to make sure that we're not only designing a part that can be made and it will meet the customer's requirements, but is something that's going to work under all the different conditions that Gary set out, particularly parts that can be manufactured efficiently, that can be manufactured well, but aren't likely to run into any issues during use.
Okay, and so you talked a little bit just mentioning manufacturing. So, are there different types of manufacturing methods, and do they impact performance?
Yeah, there's several different types of manufacturing when it comes to ceramics. You have injection molding, you have pressing. There's different types of pressing. There's casting and there's extrusion are the most common ones. Each of those has got different types of categories within them that allow different shapes and different sizes to be made. But the main thing that influences the ceramic with regards to manufacturing is the complexity of the parts that can be done. For example, you can be pressing, you may be limited. It may be able to make parts a lot quicker, but you're a lot limited on the sort of sizes and the shapes that you can make. And you then introduce risks depending on the different types of the different strengths of the press, about what Gary's mentioned before in performance, where there may be different weaknesses in different areas. Similarly, if there's very tight tolerances that need to be done, we can introduce machining after firing and after sintering in order to make parts that are a lot more complex and a lot more useful for advanced applications. However, that does add in a lot of other costs and a lot of issues like lead times and costs, particularly with regards to developing components, and risks where parts may go wrong. So one of the things we will always do is whenever we see new parts, new products, new drawings, is evaluate the actual product that's needed to look at how the best manufacturing method in order to make these components is going to be something that will be able to meet both what the customer needs and is suitable to be suitable for manufacturing.
And how do customers then balance that performance, cost, and time sort of equation?
It's about understanding what's actually critical for them. If parts are needed at a very, very short time, we have the option to make them machined fully from blanks. This can mean they can be made an awful lot quicker. However, it does cause slightly higher costs. Whereas if we know it's going to be potential higher volumes going forward, we can look at investing in tooling to be able to use an injection molding or pressing options that can be much faster and make much higher volumes without any issues, but they may initially have longer lead times due to developing tooling.
What point should someone start thinking this might need a ceramic solution?
The honest answer to that is when nothing else will survive in the application. Due to the unique mix of the properties that ceramics do have, a lot of the times they are used when other materials may not be able to survive. For example, metals may not have the strength required or not be able to survive up to the temperatures that are needed. And so that's where ceramics fills quite a unique gap in the market. And you would look at it thinking no other option could really fit within that application or within how we need this part to.
And so Gary, when you're talking to customers, do you often see that they see ceramics coming in as something to fix a problem or as a part of the an original design?
Yeah, generally ceramics are used as a problem-solving option within an existing process, possibly because an alternative material was being used that was causing application issues, and the use of ceramic material would enable improved performance or throughput within their process. We are often presented with opportunities where a customer has read that a ceramic could have a positive effect within their process and maybe eradicate the issues that they are experiencing, but generally not sure which material is best suited for their needs, which is where we position ourselves, and we like to see ourselves as experts in that area.
Okay, excellent. We're just coming to the end now, so I thought just some final sort of thoughts. So, Richard, if you could just leave the audience with one thing to think about and keep in mind when working with high temperature ceramics, what would it be?
It would be, don't overlook the little details in an application. There's, as we've touched on previously, there's so many different factors that can influence how a material is going to perform, how a part's going to survive an application. It's important to make sure that all of these different factors are understood, as that can really help when speaking with experts and looking at designing your own products, making sure that we're able to provide a fully comprehensive solution that is going to eradicate any potential issues and make sure that anything works exactly as we would hope and as you would all want the part to work.
Excellent. And Gary, can you leave us with one practical tip to improve performance or to something that can help avoid failure?
Yeah, the constant theme throughout this webinar has been twofold, really. First of all, in a thermal application, preheating the ceramic at a gradual rate, or in the case of a technical ceramic, consulting the experts during the design stage to ensure tolerances are not unnecessarily specified or edge breaks. Needs are conducive with forming methods needed to produce the part in the material required that are viable.
Excellent. Well, thank you very much to Richard and Gary. But and I'll open up if anyone has any questions. They can either put it in the Q&A, or if they want to raise their hand, I can probably unmute you if you have a question you'd like to ask either of them. So one question for either of you. Where are you seeing ceramics and high temperature ceramics is the sort of the latest thing that's sort of latest industry or latest thing that's being used for?
The surge in semiconductor, the global semiconductor market, we're seeing the requirements for ceramic being stretched, shall we say, and the parameters required being pushed further and further. And the semicon sector is certainly a driving force behind that, as well as things like EV battery, the aerospace sector, again, just pushing the parameters of what's possible and what's viable. The addition of things like 3D printing, the addition of ceramic composite type materials, and different ceramic matrix materials is certainly going to be, well, in our opinion, is certainly going to be the materials for the future.
Okay. Well, I think that was the only question that we got. So I'd just like to finally thank Gary and Richard for joining us. If you do have any further questions, please do feel free to reach out to any of us, or if you have any sort of requirements or specific applications you'd like to talk to, we're always happy to continue the conversation afterwards. So thank you very much, Richard and Gary.
You're welcome. Thank you, everybody.
Thank you, everyone.